Hi everyone, this lesson is about the exponential probability function. So this formula here gives us the function. Now lambda is a constant and different values of lambda give us different shaped functions, and lambda is, not equal to, lambda is greater than 0. It wouldn't make a lot of sense for lambda to equal 0 because then our function would just be a flat line along the x-axis, which would be a bit weird for a probability function. Now, you would recall studying discrete probability functions back in grade 11. They looked like little histograms with little rectangular blocks, and each different outcome had different probabilities perhaps. Sometimes they all had the same probability. But the thing that is important, I suppose, to note with this one, it's a continuous function. It doesn't go in little steps. It's a nice smooth curve. So x here is a continuous variable. So perhaps x is the lifetime of a light bulb. It could be 1 hour, it could be 2 hours, it could be 1.5, 1.7, 1.63, any real number along the axis. Now, what about this lambda value? Well, lambda controls not only the starting point, here the y-intercept. Imagine when x equals 0, then e to the power 0 will equal 1, and so this value here is literally equal to lambda. So we can see straight away by reading that number, I know it's a bit tiny, I'll tell you, that's 0.8. So our value of the decay constant, if you like, this constant here, governs how quickly the graph will drop down in an exponential decay. Remember, the negative sign means that it gets less and less and less. So let's have a little bit of an interactive look at this. If I go back to GeoGebra, so that's how I drew that diagram, and you can see here I have lambda set at 0.8, and I can increase that a bit up to 1. So obviously the graph starts higher up, but also now it drops down more sharply. So that's important. If I was to increase that even further, you can see, now I've got off the top of the scale, but you can see how this is virtually nothing down here by the time we reach 2. So the value of lambda not only controls the y-intercept of our function, but also how quickly it drops. So the smaller values of lambda, say that's lambda 0.1, so it's not very high here, but look, it drops down very, 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 very slowly. So that's interesting. That controls the shape of the graph and the starting point on the y-coordinate of the graph. I suppose the shape's the wrong word. They all have fundamentally the same shape as an exponential decay, but it controls how steeply the graph falls away. Now, you probably recall in grade 11 that the total area underneath one of these functions represented the probability of all the different possible outcomes that could occur, and therefore we would say the area must equal a total of 1. Now we can prove that by doing the integration here. So if I take the integral from 0 to infinity of lambda e to the negative lambda x dx, in other words, that whole area going on forever, let's just see that this does actually equal 1. So lambda is a constant, it sits there. Integral of e to the something is e to the something, and then we divide by, and now we have to think of this as a little function inside a function. Derivative of negative lambda x is negative lambda, so we divide by that. And we are integrating between the value 0 and infinity. So pretty obviously that lambda cancels there with the 1 down in the denominator. I will end up with negative e to the power of negative infinity. Subtract negative e to the power of 0. Well, that's going to be negative 1 over e to the power infinity plus 1. And dividing by a very, very large number, of course, tends to 0. So the answer is 1, as required. This thing does have an area of 1, no matter what the value of lambda. Importantly, the value of lambda here as the constant, the coefficient, has to be numerically equal, but don't forget that negative sign in the exponent. Then we get one of these special exponential graphs where the area under the graph equals 1. So we can use it to model probabilities. Now, the other thing that you would recall from probability that we often like to know is an expected value, or sometimes we call this the mean value for a probability. So the expected value for our variable, our exponential probability variable here, would be, now we used to say it was the sum of x multiplied by the probability function. Now we said it was the sum of when we were using discrete values, but of course we don't have a discrete value this time, we have a continuous value, so we will need to do an integral from 0 to infinity to cover the whole thing. Now what was our function? So our function was lambda by e to the power negative lambda x. Oh, I forgot to put dx there in that first line. So there we go. Now this is an integration by parts scenario because we have a pronumeral x, that's an algebraic term, multiplied by an exponential function here. So remember our little idea, our little rule that we used to use to help us was LIATE. Now, what did I say we have here? We have an algebraic. The algebraic is x, and we have an exponential. So now I could include that constant lambda with that bit. That's the exponential, and well, I'll also include the dx with that. Why did I do that yellow? That was silly. Now, this bit is going to be u, and this bit is going to be dv. Then we'll be fine. So let's do this. Let u equal x, and we will let dv equal lambda e to the negative lambda x dx. Du dx would equal 1, so that's nice and straightforward. Du equals dx. V would be the integral of lambda e to the negative lambda x dx. Let's see, we would have the lambda there. Oh, we did this one earlier, didn't we? It turned out to be, what did it turn out to be when we did it up here? It turned out to be negative e to the negative lambda x. Let's just write that in. Negative e to the negative lambda x. So continuing on from this point here, then I probably should have done all that stuff over there to the side, shouldn't I? Let's just push that over there slightly to the side. So now we'll say, okay, well we've got u times v minus the integral of v du. Now what have we got here? Well, u was x and v was negative e to the negative lambda x, so negative, then e to the negative lambda x minus the integral of, well, v was negative e to the negative lambda x, and du was dx, wasn't it? So what do we get? We'll have negative x e to the negative lambda x plus, by the time of that minus and that minus a plus, and we'll have e to the negative lambda x. Don't forget to divide by the derivative here, which is negative lambda. Now that's my integral, and that integral was taken from 0 to infinity. Well, when I substitute infinity into the exponential, that's effectively divide by a giant number, which comes to nothing. The same thing is going to happen here. When I substitute infinity, I'll be divided by a giant number, so that part is nothing. Now when I subtract 0, e to the power of 0 is 1, but I multiply by 0 as well, so that's also nothing. This isn't looking so great. Oh, here, finally, we will have e to the power of 0 is 1, and then it is 1 over negative lambda, so it's minus 1 over lambda. Finally, there was something. And so it turns out, and remember, this was the expected value. The expected value is 1 over lambda. How interesting. So let's go back to take a little bit of a look at our graph here. Now, why don't we set lambda equal to 1. There it is. So lambda equals 1. The expected value is 1 over lambda, so 1 over 1 is 1. So this will be the expected value, 1, for my probability variable. Now, of course, it might come out higher than that, it might come out lower than that, but that's interesting, isn't it? Now, how do we find the probability of something occurring? We find the area under the graph between two limits. So there's my integral from 0 to, well, way out there at 15, comes to 1. What if I bring my upper limit in a little bit? What if I bring that into there? The chances that this variable will lie between 0 and 1 is 0.63. What if I increase that a little bit to, I'm trying to stop on 0.5. There. The chances that this variable is between 0.5 and 1 is 0.24. So we can find the probability, you can answer these probability questions by calculating areas under these graphs, by calculating integrals. Perhaps that's enough for this one, and in the next video I will do an example of such a calculation. Thanks for watching.